Once we have this idea of a multiplicative identity, we can talk about inverses. So in high school, grade school, kindergarten, I don't know where it's talked about. I know it's not really kindergarten. If you wanted to solve 4x equals 1, think about what you're doing. You're trying to figure out what's the real number that you have to multiply by 4 to get 1. So this 1 here is the identity. And of course, your answer is going to be 1/4, which you write as 4 to the negative 1. That notation means that it's the multiplicative inverse, 4 to the negative 1. So it's the thing that you have to multiply 4 by to get 1. Not every number has a multiplicative inverse. In fact, with the reals, there's exactly one number that doesn't. Okay, so 0x equals 1 has no solutions. This is why dividing by 0 is not defined, is that 0x equals 1 has no solutions. Okay, so not every number has a multiplicative inverse. The same is true of matrices. What we're going to want to do for matrices is we want to find the matrix, let's say B. I'm using B differently than I did before, but let's find the matrix B so that A times B is equal to the identity matrix, where let's say A is the matrix 1, 4, 1, 5. B is the, just say a generic matrix A, B, C, D. And I is the 2 by 2 identity matrix 1, 0, 0, 1. This is exactly the thing that we were doing up here. We wanted to know, we start with some quantity. We want to multiply it by something so that we get the identity. So again, we start with some quantity. We're multiplying it by something so that we get the identity. That's what we want to do. And we're going to denote whatever matrix we get B here as A inverse, if it exists. We'll talk about when it exists in general, but I want to, for now, find what's the inverse of this matrix 1, 4, 1, 5. So I'm not going to do anything fancy. I'm going to do exactly what we did before. We're going to multiply A times B. We'll get 4 equations, 4 unknowns. We'll solve them. We'll move on. So A times B, being the identity, means that we want to solve 1, 4, 1, 5 times ABCD equals 1, 0, 0, 1. And so A times B, capital A times capital B, is going to be the 2 by 2 matrix A plus 4C, B plus 4D, A plus 5C, B plus 5D. That's going to be equal to 1, 0, 0, 1. And then we have 4 equations, 4 unknowns, but really you can think about it as 3 equations, 3 unknowns if you like. I'm sorry, 3 equations, what am I talking about? You have 4 equations, 4 unknowns. You could think about it as 2 equations, 2 unknowns twice, because when you write down what equations you have, they separate. You have an equation in A and C. So A plus 4C is 1. A plus 5C is 0. B plus 4D is 0. B plus 5D is 1. So let's solve each of these systems, and you can do this again whatever way you like. Because this matrix works out so nicely, I'm just going to do this kind of not using any linear algebra methods. I'm just going to solve this algebraically. So if we subtract the top matrix, or the top equation from the bottom equation here, I'm looking at these 2 equations, we're going to end up with C is negative 1. And if C is negative 1, that means A is going to be 5. And let's just check that that's a solution. We know that 5 minus 4 is 1, and 5 minus 5 is 0, so that's perfect. Likewise over here, we're going to take the top equation and multiply by minus 1, add that to the second equation. So we're, in a sense, taking the second equation and subtracting from it the first equation. We end up with D equals 1. And if D is 1, B has to be negative 5. Okay, negative 5. Is that right? D is 1. This doesn't work. Why doesn't this work? So D is going to be 1. Oh, B is -4. That's why it doesn't work. So B is -4. So always check. So I just checked it and I didn't, this top equation didn't work out. If B is -4 plus 1 times 4, so that's -4 plus 4, that's 0. And -4 plus 5 is 1. So everything's fine. Here's our solution. And so it turns out that A inverse is going to be the matrix A, B, C, D. So that's 5, -4, 1, -1. Okay, good. So that's A inverse. And let's do this in general. So let's find A inverse in general. And to do this in general, I want to actually walk through another process to find the inverse, just to explain how this is going to work. So I want to find A inverse. Let's actually do this previous example one more time. We wanted to solve AB equals I. And it turns out there's a general way that you can do this. You don't have to solve 4 equations with 4 unknowns in general, and that's only for 2 by 2 matrices. If you had 3 by 3 matrices, you'd have 9 equations and 9 unknowns. But in general, what you can do is the following. You can augment your matrix. So here's the process. You can augment the matrix A with the identity of the appropriate size. Here, by the way, I'm assuming A is square, just so that that's clear. We're only talking about inverses for square matrices. You can't talk about inverses in general for non-square matrices. And by square, I mean the number of rows and the number of columns will be equal. So I'm going to take A, put it in a matrix, and then put the identity on the other side of our augmented matrix. And what we're going to do is we're going to do row reductions until we get the identity on the left. And we're going to end up with some other matrix on the right. It turns out that that second matrix, so it turns out that the second matrix B is going to be the multiplicative inverse of A. It's going to be A inverse. So let's just try it. Let's take our matrix A that we had before, which was 1, 4, 1, 5. I'm going to augment it with the identity. In this case, A is a 2 by 2 matrix, so I augment it with the 2 by 2 identity. And then what we're going to do is we're going to manipulate this matrix and do row reductions until we end up with the identity on the left side. So in our case, we're going to take row 2 and subtract from it row 1. And row 1 will stay the same because we're not messing with that. And what we're going to get is if we take row 2 minus row 1, we're going to get 1 minus 1 is 0. 5 minus 4 is 1. 0 minus 1 is -1. 1 minus 0 is 1. And we're actually almost done. On the left, we just have to deal with this 4. So we're going to take the second row, multiply by -4, add it to the first row. So our new row 1 is going to be row 1 minus, a stray mark is bothering me, sorry. So it's going to be row 1 minus 4 row 2. And what we're going to get then is the bottom row will stay the same. The top row is going to be 1, 0. That was by design. That's why we picked -4. And then let's see, -4 times -1 is 4, plus 1 is 5. -4 times 1 is -4, plus 0 is -4. So we end up with A inverse being this matrix 5, -4, -1, 1. And it turns out, let's just double check. Let's verify that A times A inverse really does give us the multiplicative identity. So A being 1, 4, 1, 5. A inverse, us having found it twice now, is 5, -4, -1, 1. Okay, and Then what we're going to do is multiply. So we're going to get 1 times 5 plus 4 times negative 1 is 1. Negative 4 plus 4 is 0. 5 plus negative 5 is 0. And 1 times negative 4 plus 5 times 1 will be negative 4 plus 5 is 1. And that really does give us the multiplicative identity there. So that's why those are inverses. It turns out, this is just something to know in general. This is something special about inverses and something special about the identity. It turns out that A times A inverse is going to be the same as A inverse times A if A inverse exists. So it turns out that if you multiply A by A inverse, it doesn't actually matter if you multiply on the right or the left, you'll get the same thing. Also, the identity commutes with all matrices. So if you were to have A times I or I times A, that's going to be A for square matrices. For square, and again by square, I mean that the number of rows and the number of columns are equal. For square matrices. Okay, so these are special matrices that do commute, and we'll talk a little bit about other matrices, more matrices that also commute, either with each other or with anything else. Okay, so that is that.